I took the first 100 prime numbers, squared each of them, and then added them all up. And now I'm going to ask you, what is the remainder when this sum is divided by 6? If you're not familiar with number theory, then this problem might be a little bit tough. But if you're not, then don't worry. I'm going to go over the solution thoroughly, and you might learn a thing or two about prime numbers. So hop on. So, when we have a complicated sum like this, it's best to maybe just consider one term. I mean, prime numbers and squared numbers, right? Not the easiest things to, manipulate. So just consider one term. So each term is just a prime squared. Now let's try to derive a general property that any p squared has for any prime p. Well, this is a question regarding division by 6. So it might help to first exclude 2 and 3 because 2 and 3 are, factors of 6, and that might make it awkward to derive a general property that p squared should hold. So let's just consider 5 squared, 7 squared, all the way until 541 squared. We know that each of the primes 5, 7, all the way to 541, they must be relatively prime to 6, meaning that they share no common factors with 6 other than 1. So if that's the case, then let's try to do some casework. What are some forms that p can take? Well, if p is a prime number, then obviously it cannot be a multiple of 6, so it must be, for instance, 1 more than a multiple of 6. And there are indeed prime numbers which are 1 more than a multiple of 6. Now, obviously, k is an integer, this means. So if this is the case, then is this valid? Again, yes, of course. However, is it possible for p to equal to 6k plus 2 more than a multiple of 6? No, because that would be even, and we're not considering 2 or 3, so no. And similarly, 6k plus 3 wouldn't work as well. 6k plus 4, that's even, so what else? Well, there's definitely 6k plus 5. That is also another form that a prime number can take if it's not 2 or 3. So with this in mind, are there more? Well, you might be thinking, what about 6k plus 7? Well, this is actually redundant. This is the same as this, because this can be written as 6k plus 6 plus 1. And this is 1 more than a multiple of 6, which is basically congruent to this case. So now that we have all our cases, let's square both equations, because we want to find a property for p squared. So if we take this first equation and we square both sides, we would have on the left-hand side p squared, and this is equal to the right-hand side squared, which is a binomial squared, so you get 36k squared plus 12k plus 1. Now analyze this a little bit. Notice that 36k squared, it's a multiple of 6, obviously, and 12k is also a multiple of 6. So we just have a plus 1 here, meaning that under this case, any prime squared with this form is always 1 more than a multiple of 6. Okay, that's nice to know. But what about this case? If we square both sides of the equation, we get p squared is equal to 36k squared plus 60k plus 25. Well, firstly, 25 might look like a big number. But if you consider splitting up 25 as 24 plus 1, then take a look at this. Notice that 36k squared is, divisible by 6. It's a multiple of 6. This 60k is also a multiple of 6. And 24 is a multiple of 6. So we just have a plus 1 here. So therefore, under this case, again, a prime number squared is a multiple of 6 plus 1. So this would mean that any prime number that is not 2 or 3, any prime number with those restrictions is always going to be 1 more than a multiple of 6. So therefore, we see that all of these terms, right? When you divide each of these terms by 6, they will have a remainder of 1 because they are always 1 more than a multiple of 6. There is a formal way to write that a square of any prime number must leave a remainder of 1 when divided by 6. There is a formal way to write that, and that is to write p squared is congruent, that's what this sign means, congruent to 1 mod 6. And this basically reads, you take a prime number squared and divide it by 6, it must leave a remainder of 1. So this is, just a short way to express what we've been deriving. So with this fact in hand, let's consider the sum from 5 squared all the way to 541 squared. We know that each of these must leave a remainder of 1. Each of these terms must leave a remainder of 1 when divided by 6. So we can actually write that 5 squared is congruent to 1 mod 6. 7 squared is congruent to 1 mod 6. And all the way to 541 squared is congruent to 1 mod 6. And we want to find, if we were to add all of these numbers, 5 squared all the way to 541 squared, if we add all of these up, then what is it congruent to mod 6? Well, in modular arithmetics, you can actually add both sides of the congruence. So this side, we have our desired sum. I'll just call it S. This is congruent to 1 plus 1 plus a bunch of 1s. So how many 1s are there? Well, this is the third prime. All right, so I'll use blue. So this is over here the third prime, and this is the 100th prime. So altogether, if you were to count this, there would be 98 terms being added. So there are actually 98 1s being added. So on the right hand side, we have S is congruent to 98, and then mod 6. Now 98, that's not really what we call a residue of 6, because no number divided by 6 leaves a remainder of 98. The reason is because you can divide 98 more to eventually get a remainder smaller than 6. If you were to divide 98 by 6, then what is its remainder? Well, it's 2. So we know that 98 itself is congruent to 2 mod 6. And there we go. We see that the sum from 5 squared to 541 squared, the prime squared, this sum over here is congruent to 98, which is congruent to 2 mod 6. So altogether, this entire sum, it leaves a remainder of 2 when divided by 6. Okay, so we've only dealt with the part underlined in red. What about 2 squared and 3 squared? That's pretty easy. We see that this over here, this underlined in red part, this is congruent to 2 already. And then now we just have plus 2 squared plus 3 squared mod 6. So now we know what 2 squared and 3 squared are. They're just 4 and 9. So altogether, this is congruent to 2 plus 4 plus 9 mod 6. And this would be congruent to 3 because if you were to add them all up, this would indeed give you 15, and 15 is congruent to 3 mod 6. So we see that this entire sum, when you divide it by 6, yields a remainder of 3. Okay, so that's our answer. 3 is our answer. While we did get our answer, I do want to say that if you are new to modular arithmetics, then I highly recommend you learn about them, because they are very powerful tools for number theory related problems, especially those regarding prime numbers, some integers squared, even cubed. They can be very powerful problem solving tools. So with that note, I want to thank you for watching this video. If you found this video interesting, then please do consider dropping a like and subscribing. Thank you very much. Bye.